you very much for your time. What I'm going to do is demonstrate the ICD Stackup Planner. And before we begin, I simply would like to show you or give you a general overview of what this tool is all about. This tool is kind of like a Swiss Army knife for those people who are doing layout design. It consists of really two major functions. First and foremost, the Stackup Planner, and secondly, this feature called the PDN Planner, or PDN standing for Power Distribution Network. What's interesting about this tool is you may see that these seem somewhat unrelated to each other, but as a matter of fact, what this is trying to do is address impedance issues. In high-speed design, we're going to have impedance issues not only on our traces, but also on our power distribution network as well. And you may say, well, what's a power distribution network? It is simply our power supply and our power planes that are on our boards. And so we want to make sure that we can address and mitigate those impedances, or at least control them, especially if we're doing signal traces. And that's pretty much what we're trying to do over here in the Stackup Planner. And we'll talk a little bit about this where I've got my cursor. We are on the cursor here is located in the characteristic impedance column, and then right next to it is the edge coupled differential impedance column as well. On the PDN side of things, and again I'll mention this, that there's another video that goes into great detail. What we're trying to do over here is we're trying to reduce the impedances as much as possible. So if there's any AC noise that is on our power distribution network, no matter what frequency it is, we're able to get it off our power supply and into the ground plane as quickly as possible, so that that noise does not make its way to the components and causes more issues with our signal integrity. But again, covered in another video. Let's jump over here to the Stackup Planner. Now you may be saying to yourself, well, any EDA tool out there has obviously a Stackup capability, or you can call it a Stackup Planner. But what this one does over here, which other ones kind of fall short of, is first and foremost that they can handle the characteristic impedance equation, so that we know what the rules are going to be when we want to figure out what the trace space and the trace clearance is to get very specific impedances. In addition to that, there's also material information that's provided here as well. And if we want to take a look at the material library, we can simply click on it here, and we can see that there's well over 30,000 materials that are in here. Now, yes, you can go through here and pick and choose things that you think will work best for you here. You always want to have a conversation with your fabricator after you pick them to make sure that, number one, it's not cost prohibitive, number two, that there's no lead time to it, and number three, that it doesn't cause big issues for their processes. Because obviously there's FR4, which has been the standard material for many, many years, but in high-speed design we need something with a better dielectric constant. But usually when we pick other materials with better dielectric constants, there's something we have to sacrifice as a result of that. So we have to be very careful about the ones that we pick. And this tool really is more so that you can have an intelligent conversation with your fabricator at the beginning of the layout. This is not something you want to present to them at the end of the layout and hope that it will work, because you're going to put both yourself and the fabricator at great risk in terms of accomplishing what you're trying to do. But all the materials are here. One of the nice features about this is that if you don't even know what manufacturers are out there, well, it's all listed here. And once you find a material that might be of interest to you, you can always go onto their website and find that material that you have an interest in, find their data sheet there, and of course have a conversation with the fabricator to determine if that material is the best selection for what you're trying to do. Now, by the way, if the fabricator is already going to select all this stuff for you, well, they can provide you this information as well, and it's a matter of you simply looking it up and adding this information into the Stackup Planner. If there's a material out there that's not in here, which would be rather surprising given there's over 30,000 materials, but companies do come up with new materials, you can certainly add those materials in here as well. There are certainly sort features in here, so if we right click here, we can sort on based on certain columns. We can also do some filtering as well. Obviously with the number of entries in here, we probably would want to do that type of search. So just letting you know that this library does exist, and it's a good starting point if you are trying to look for materials above and beyond FR4. All right, and then in addition to it, so obviously we have our Stackup over here. Now, impedances are an interesting creature, because impedances are completely reliant upon the board Stackup itself. And as a matter of fact, some people may think that, well, I've still controlled the width of the trace, and I might be able to control the space of the trace on my own. But that's not necessarily true, because if we really think about our Stackup planning, in addition to things like the dielectric constant or the height of the dielectric, or even the trace height or the trace width, we know what the impedance is. Okay, and so as a result of that, the one thing that we can readily control outside of the Stackup itself is the width itself. So we shouldn't just go in thinking, well, I can create a Stackup and I can create separate rules, and that they are disconnected or somehow not associated with each other. And that's not necessarily true. They are very much associated with each other. And that's why these columns up here, like copper thickness, trace clearance, trace width, and so on and so forth, are given to us so that in the end, we can actually come up with not only a Stackup that's realistic that we can provide to our fabricators for review, but we can also get characteristic impedances here that we want, and in turn use this information like the trace clearance and the trace width to create our rule set. And so we'll kind of demonstrate that here in just a moment. As you notice over here, there are a number of predefined layers. Feel free to use these. All right. They're viable layers, but if you have a different layer set that you want to do, you can certainly do that as well. As a matter of fact, I'm going to demonstrate that right here and right now. If I wanted to copy this because I want to do something somewhat different, I can do a shift click, and then I can right click here and I can say copy, and if I want I can create a new layer set here. Actually, let's create a brand new one that's completely blank, and then I just simply need to click paste and it'll drop it in. But let's start one from scratch. Let's say, for instance, there's one that's a very different layer stack up here. And yeah, you can move these things by right-clicking and moving and swapping rows and stuff like that. But it becomes a little difficult. And so obviously, and it's not difficult because the tool doesn't make it difficult. It's just difficult because you got to keep track of your prepreg and your cores and which one's a plane and which one's going to be a signal stack up. So sometimes it's a lot easier here just to start with a clean slate. And that's what we'll do here. So I'm going to right click here and I'm going to rename this stack up to demo. So we'll do that just fine here. And let's begin. So though don't have a lot of time here to really talk about the differences between core and prepreg and other materials. I guess you're going to get a crash course lesson in the different types here. But if you are interested in more information about this, we at 9.Connects did do a seminar on this, actually a webinar on this back in September of 2015, and it is called the Stackup, and we did actually use the ICD tool to demonstrate a few things, though there's a number of PowerPoint slides and it goes into a lot more details about the concept of Stackup. But with that, let's start over here. I'm going to create an 8-layer board. This is a common type of board that we use here at 9.Connects if we were going to do a high-speed design. So let's start off with the very beginning here. I'm going to right click here, and now at this point it doesn't really matter if I insert above or below because there's nothing really to insert above and below. It's the first one here. But what I'm going to insert in here is a core. And a core material is a hardened material. It's a dielectric material, so it's not conductive, and it usually has a copper on the top and on the bottom. Actually, not usually, it always has a copper on the top and a copper on the bottom. And so once they have this material, they'll etch off the copper based off of whatever pattern you have, and depending on what layer it's going to represent on the top and on the bottom. Now, let's put some copper representations over here. So what I'm going to do over here is I'm going to put on a, I'm going to insert above here, I'm going to put on a plane, and actually I'll move this one over here, and I can drag it up very easily. So I'm going to have my plane up here on the top, and then on the bottom I'm going to insert below a signal layer. Now, for our purposes, is there really a difference? The answer is no. Really, just planes are going to have a lot more copper because they're going to represent voltages, whereas signals are going to, obviously, most of the copper is going to be etched off for traces over here. But we now effectively have over here a core material and a representation of two of our materials. Now, what I'm going to do over here is I want another layer above this here. And obviously I'm really not going to put another core here because that's a material all its own, the core with the copper on the top and on the bottom. So I do need to have another dielectric here, so I'm going to insert above, and now I'm going to put a material called Prepreg. And the only difference really between core and Prepreg is that Prepreg is a material that hasn't been hardened yet. It's kind of soft, a little bit mushy, and once you apply heat to it, it actually liquefies, and it now actually becomes a resin or a kind of a type of glue for the simplest of terms here. Right, so now I have my prepreg, and now I need to get another layer on here. So again, I'm going to do assert above, and I am going to put here a signal layer. And this is actually going to represent my top layer on my board. And then lastly, I need something that is called the solder mask. And the solder mask is really there for no other reason than, number one, cover over the copper traces that are not requiring any type of solder. So when we put solder on our pads, we don't want to wick down the traces. That's first and foremost, because otherwise we'll lose all our solder. But secondly, we don't want our copper to be exposed to the air, because copper has an amazing way of reacting with the air over time, and obviously it's going to cause some reliability issues. So we want to make sure we do have a solder mask on the top over here. So notice as we're putting these things in, we're starting to see some values here, and we'll talk a little bit more about those as we go along. Now on the bottom side here, I am going to actually put down another prepreg, okay, because again we're dealing with the core material above it. And then below here, I'm going to put down a plane, and then I'm going to put my core material down here as well. So again, we got core material separated by prepreg, or if it's on the top, we can do something called a copper foil. And the copper foil can, once this has been hardened, then they can actually etch off the copper foil. It all depends on how the fabricator is going to do this. And that's why, again, it's really important that you have a conversation with them, because how you get this stack up together is going to be very dependent on their processes. What I'm going to do over here on this last one is I'm going to put a copper here below. It's going to be actually a plain copper. So now I've got half my board done here. All right, and you'll notice that, just as a side note, I've got two planes over here. Now why would I have two planes here? And then on the bottom here I would have my pretty much a duplicate of what I've got here on the top. Well, these planes over here are to make sure that whatever activity is going on the top here doesn't bleed down to the bottom in terms of signal integrity issues, and vice versa. We don't want this stuff to start the noise of them to cross over to each other so that they impact each other. So that's why we put these two planes over here. And as a matter of fact, and I'll go into a little bit more detail about this when we talk about the vias, what we want to do here is ultimately keep as much of our traces that has to do with those things on the top, between the top layer and layer 3. And yeah, we may have to send traces down below to the bottom, but we want to kind of minimize the amount of traffic that goes between the top and the bottom as much as possible. And we don't necessarily want to have a bunch of different pipes that go, let's say, from 1 to 3 and 3 to 5, and or actually it wouldn't be 5, but let's say 3 to 6. Some of them aren't even manufacturable anyways, and some of them are going to lead to signal integrity problems, and we don't necessarily want to go down that particular path. One of the things that this tool is going to allow you to do is to set up stackups and vias any way you see fit. But again, you got to bring them to the manufacturer, and again, your fabricator, to make sure that what you're putting together is manufacturable. Okay. Now, I'm going to cheat here a little bit, but it's the power of the tool. Obviously, I can continue to draw the same thing down here by right-clicking and inserting below. But what I'm going to do here is I'm actually going to take this one and I'm going to cut it. I could also do an undo as well. And the reason I'm going to do that is I'm going to use a mirror feature here. So I'm going to click on, hold down my Shift key, and I'm going to click on the top and the bottom here so that I can select all of these. I'm going to right-click and I'm going to mirror the stack up. And now I have a complete mirror here, and now I have my 8-layer board done. Now, let's talk about the impedances here and what can we do to kind of control those things. Because again, our board stackup totally controls these. Most signals are going to want to have a 50 ohm impedance, and if they are differential pairs, are going to want 100 ohms. Now, if you want something different than that, you can always actually click on this here. So if you wanted to actually try to get some of these to 85, you can set up these things in such a way that you can do it. Obviously, when you do that, you have to be careful, because if you start changing the layer stack up over here in this new pair, it will impact pair 1. But the idea behind this is that you may have different rules where the copper, well, let's say copper trace and the copper width over here could be changed so that you could get different impedances, and then those rules could be applied specifically to those type of traces. But again, if you start changing dielectric constant, the thickness or the copper thickness here, you're going to impact everything. So at least there is the ability to create different rule sets of clearance and width based upon different impedances you may need. For example, USB, I believe, needs 85 ohms, so you could set that as such. But for our demonstration here, let's just assume that we need 50 ohms and 100 ohms here. So let's take a look at the things that we can control here. Obviously, we can change the dielectric constant. Right now, it's defaulting to FR4, which is approximately 4.3. The better or the smaller the dielectric constant, obviously, the better for it. But we can also play with the dielectric thickness as well. And that's where we have usually a lot of opportunity, unless you're dealing with a board that's got some really restrictive height clearances. But generally speaking, we want to get board thicknesses that will work for us. Here's a board thickness of 42. The default one is about 62 mils, which represents about 1/16, which has been the tradition. Does it have to be that thickness? No, it could be thicker, it could be a little thinner. just keep in mind that the board thickness is, number one, there has to be a rigidity to it so it holds the board together. And number two, it also impacts the size of your vias. The thicker the board is, the wider your vias are going to have to be. So if you got a dense board design, yeah, you can go up in thickness, but also you're going to have to increase your via holes in order to allow for plating. All right, so let's play with this over here. We have a characteristic impedance of 64.96. This is a little high. Okay? And by the way, one thing I'll note, you don't necessarily have to have this at 50 ohms. Okay, and 50 ohms dead on the money, because there are manufacturing tolerances. There's humidity in the air, depends on the operator, depends on the calibration of the machine that day. How much time, maybe they waited a second too soon, waited 10 seconds too early, you don't know. So, and plus you're dealing with chemical etchings as well on the copper, so there's a bit of a potluck to it. They're always improving those manufacturing tolerances, but generally speaking, if you try to get this 50.0 on the money or 100.0 on the money, you're kind of wasting your time. So you want to get it in a near ballpark figure, and that's going to be good enough. All right, so what can we change over here? We can change the copper thicknesses. We can change the trace clearances, and as we change them, so for example, the trace clearance, let's just say I want to see what happens when I do a clearance of 8 over here. Well, notice that it didn't change our characteristic impedance for the single, but it certainly had an impact on the edge couple. All right, and this is going up now to 115, where it was originally 105. So maybe I need to want to reduce that. So that's another feature I can do. Now I can kind of play around with these things, but one of the neat features of this tool here, and I'll bring it up here, is this thing called the Impedance Plots. And the reason why this was brought up is for the very reason that, yeah, we can play some games with this and we can do some guessing to it, but it's really nice to take a look and say, well, based on the information I may have on this particular layer, if I want to try to get this down to 50 ohms, it may behoove me, at least from a trace width point of view, to try to get this to at least 5 mils. And for trace thickness, okay, so this is trace width. For the trace thickness, which is copper height, and this is what I could do as well. So notice the trace thickness, so the copper height, isn't going to have much impact on this. So sometimes people want to throw more copper on it, and that's certainly good for thermal purposes, and that's certainly good for power, but that may not necessarily buy you a whole lot in terms of impedance control. There's also trace clearances as well, so you can see how much trace clearance you're going to get as in terms of your impedances. And then also for differential coupling, they put 2 of these on here. So for example, at 8 mils here, I will get an impedance here, the blue trace. Let me pull this out here so you can see a little bit better over here. The trace clearances, okay? So at 8 over here, this is what the trace clearance is going to be. And then here's for the dielectric thickness. So they're trying to show you what's going to happen for both of those factors here, trying to bring them together. So you can certainly use this over here in order to improve the values that you're getting, so you're not totally guessing in the dark. Though, honestly, it's been a good academic investment here to play with these things to see what you get, because then you get a better feel for things. Say, what happens when I make this bigger? What happens when I make this smaller? But that impedance plot certainly helps it along as well. One of the things I have found certainly is the dielectric thickness plays a big role with it. So if I even put this up to 10 over here, you'll see that it definitely plays a big role with this. And you can change these to your heart's content. Now, for the trace, the copper thickness, I am going to make 1.4 because that's 1 ounce of copper. The 0.7 is ½ ounce copper. The interesting thing about copper weight is that it's based off of weight. They call it ounces. And it's based on taking 1 ounce of copper and how much you could spread it, or the thickness that you get if you spread it over 1 square foot of material here. So I believe 1.4 is basically 1 ounce of copper here, and that's fine, and that's pretty typical. You could go with ½ ounce. That's why you saw 0.7 in there. And notice it, we got a little bit of an improvement on the edge coupling. Actually, that's really good here because it's as close to 100 as possible. But we also have characteristic impedance issues here that we've got to improve. So what can we do about this? Well, to get this to go down a little bit lower, we can change our trace width, and maybe we can go over here to 6. Okay, and you'll notice that this obviously changed, but we also got a little bit of a drop over here. So we can keep playing with these to some degree until we get this to the desired area that we want it to be. Now also notice here that just because I played with this, none of these are going to change as well, because we're dealing with the difference between microstrip and strip line. This tool has a field solver in it. So as a result, based on all the material information that you provide over here, it can give you very accurate readings as to what each one of these layers is going to do. And that's a good thing, because in most rule sets you can go in there and you can make those changes accordingly based on the certain layers. If you're on layer 3, this is the rule. If you're on layer 1, this is going to be the rule. And that's a nice ability to have here. The last thing I want to do here, because I don't want to spend too much of your time on this, and if you're interested in playing with this, let us know. We can get you a demo copy, and you'll probably have this thing mastered in about an hour or two. It's a very easy and intuitive tool to use. The last thing I'll talk about here is the vias. So you'll notice that by default we always have a through-hole via. In high-speed design, we generally don't want to have vias all over the place. We also have to be very careful about where we put them, because we don't want to have manufacturing issues. So what we're going to do is we're going to say, well, you know what, on the top over here I've got my top signal, and I want to dedicate layer 3 to any signals that I can't fit on the top, but I don't want them to go really beyond the 4th and the 5th layer, because I don't want them to really interfere with these things on the bottom. So I want 1 and 3 to work together, and I want 8 and 6 to work together. Okay, so we've already got our through hole, and obviously you need to have a through hole, and it even recognizes that by default. So I am going to enable this, and I'm going to say, hey, start on layer 1, and then I'm going to say stop on layer 3, and then as a result of that, it's already going to give me the finished hole sizes, and I'm going to put this to 8 just to kind of keep it in continuity with it. Now there's an aspect ratio over here, and this is really simple. There's, as I mentioned before, you have a thickness of the board versus the hole, the diameter of the hole. And as the board gets thicker, in order for it to be drilled and properly plated with copper, you got to have a bigger hole. And most companies can easily do anything that's below a ratio of 8 to 1. Once you get from above 8 to 1, you start thinning out the companies. A lot of companies can still do 12 to 1, but once you start getting up to something like maybe even 50 to 1, which is pretty extreme, you're probably dealing with maybe 1% of the companies out there, and it's going to be a lot of money. Also notice that this declared this to be a blind via, so it recognizes the fact that I'm going from a top layer to some type of mid layer, and that is defined as a blind via. So it has that recognition here as well. Now I could actually also put one between 8 and 6, but instead I'm just going to mirror it here so it knows to put it between 8 and 6 because I'm pretty happy with the way this is set up here. So I'm going to press save, and now I've got this set up here and I'm ready to go. Once I'm done with all of this and I want to get this out to somebody, there's a couple of ways to do this. I can export several ways. Actually, I can use CSV. Obviously, I can do Excel, and I can do this in text. If you have some of these, if you have any one of these tools in here, you should be able to export it out there. And you also, when you purchase this, you just let us know which particular export tool that you need, and that is the one that's going to be activated over here. Also, it can export into the IPC 2581. That's the new specification from IPC specific to fabrication. It's basically a universal one, and a lot of people don't realize this, but both Gerber and ODB++ are actually proprietary formats, though Mentor Graphics and I think UCAMCO are the ones that own those. They generally allowed people to use them without royalties. But the IPC didn't really like the fact that they did have an ownership, so they came up with their own version of it, and it's being widely adopted. And this tool does export Stackup information to the standard. So that's the tool here. And again, as I mentioned earlier on, if you're interested in getting a demo of this, feel free to contact us here at 9.Connects, and we'll be more than happy to get you that demo. And again, it's a very simple and intuitive tool to use. You'll probably have yourself wrapped around this and understand what's going on here in probably about an hour or so. Well, thank you very much for your time, and please do look at our PDN planner video.